Question 16 says a tall cylindrical vessel with an ideal gas is located in a uniform gravitational field with a constant free fall acceleration. The temperature of the gas varies along the height h such that its density is the same throughout the volume. The modulus of temperature gradient dt by dh, in fact mod of dt by dh, varies with molar mass m of the gas as, well, basically you have to find how in this particular case modulus of dt by dh varies with molar mass m of the gas. Now it's given that the free fall acceleration is constant, so that means we can take g to be a constant in this particular case, and density is also same throughout the volume, whereas temperature of course varies with h. So first of all, let's write the expression for variation of pressure of the gas with height h. In fact, we know that dp by dh can be taken as minus rho g, where of course h is taken positive in the upward direction, okay, and well, the acceleration due to gravity is in the downward direction. So this is the expression, right? And well, we have to bring in dt by dh, etc. So let's look at the expression for P. Pressure P using the ideal gas equation can be written as nRT by V. We can do that. The ideal gas equation. Now we have to bring in molar mass, etc. So let's, and also of course density. So you see, we can put n, the number of moles, as the total mass small m divided by capital M, and this is for n, and then into RT by V. And further we can see that small m by V is density, which has been given as a constant in this particular case. So P is also equal to, that means rho RT by capital M, where rho is the density of the gas. Now in fact we can differentiate both sides with respect to h. So it gives us that dp by dh will be then equal to, we can see that rho r and capital M are going to be constants. So rho r by capital M dt by dh, and dp by dh we saw from the equation taken from fluids as is equal to minus rho g. So this tells us that the value of dt by dh itself is equal to minus capital Mg upon r. And so now we have the dependence of mod of dt by dh with capital M. We can see that it is clearly proportional to capital M, and that means for question 16 option 3 is correct. Let's go to the next question now. Question 17 says a solid rectangular sheet has two different coefficients of linear expansion, alpha and 1 point alpha along its length and breadth respectively. The coefficient of area expansion is, well, so let's take, obviously the question is from the topic thermal expansion. Let's say this is the rectangular sheet, length is L and breadth is B. So area is L into B. Now as the temperature is increased by delta T, the length and breadth both increase, and the new area is A plus delta A, which is equal to new length, and that new length is L into 1 plus alpha. So if we consider that the coefficient of linear expansion along length is alpha, then the new length will be L into 1 plus alpha delta T, where delta T of course is change in temperature, and similarly the new breadth will be B into 1 plus 1.5 alpha as given in the question. So it is 1.5 alpha delta T, and this of course will simplify to LB, and let's look at the other terms. This is 1 plus 1.5 alpha delta T plus alpha delta T, and plus another term power 2 of alpha and also delta T. Now that term we can neglect, okay. So this term, which is having alpha square delta T square term, that will be very small, it will be negligible. So it's negligibly small term. So that means we can take the new area as LB into 1 plus 2.5 alpha delta T, and so that means that the change in area delta A can be written as original area, which is LB, into 2.5 alpha delta T, and then we can equate this to A into coefficient of area expansion beta into delta T, and by this comparison we get the value of beta as 2.5 alpha. So for question 17, option 3 is correct. Let's go to the next question now. Question 18 says a metal rod has length L, area of cross section A, Young's modulus Y, and coefficient of linear expansion alpha. A compressive force F is applied at the two ends of the rod, and simultaneously its temperature is increased by delta T such that the net change in its length is 0. The value of delta T is. Well, we can see that this question combines the concepts of thermal expansion and mechanical properties of solids. So there is concept of thermal stress also involved here. So what is happening here is that the temperature has been changed, increased by delta T. So if it was free to expand, it would have expanded, but by application of compressive force F, that expansion has been prevented. So that means the effective compression in length due to application of compressive force is in fact L alpha delta T, right? So this is the magnitude of delta L. This is the increase that would have happened, but because of application of force, it's not being allowed to happen. So this effectively is the compression in length. And so if we write the equation of Y is the compressive force F divided by the area of cross section A into delta L by L. So in this particular case, what we have is F by A, and this term is L alpha delta T by L, and so we get Y is equal to F by A alpha delta T, and we can see that delta T is very easily seen as F upon alpha A Y. And if you look at the options, it is matching with option 1. Let's now go to the next question. Question 19 says a monatomic ideal gas is taken through the cyclic process ABCDA as shown in the PV graph. The efficiency of the cycle is close to. Well, clearly the question is from the topic thermodynamics, and if we look at the process, we can see that in process AB, heat is being absorbed by the gas. Let's say the heat absorbed is Q1. Why so? Because it's a case where the process is isochoric but pressure is increasing, and so temperature is increasing, and so the internal energy is increasing, and that change in internal energy is in fact equal to Q1, the heat absorbed by the gas. The process BC also heat is being absorbed by the gas. Let's say the heat absorbed is Q2 because it's a case of isobaric expansion, whereas in process CD heat will be rejected by the system, and let's say it rejects Q3 amount of heat. Similarly in process, well, why it is rejecting heat in process CD? Because it's a case of, it's an isochoric process in which pressure is decreasing and so temperature is decreasing. So Q3 amount of heat will be rejected by the system. And finally the process DA is isobaric compression. So here also say Q4 amount of heat is being rejected by the system. So the efficiency is simply the work done in the cycle divided by heat absorbed Q1 plus Q2, right? Now we can easily find the value of work done by the gas by taking area of the rectangle, and the area of the rectangle we can see that it is P0 into 2V0, so that means it is 2 P0 V0. That is the work done in the cycle by the gas. And let's now evaluate Q1 and Q2. So it's a isochoric process, the process AB. So Q1 is N. CV for an monatomic gas is 3R by 2. delta T. So that means it is TB minus TA, that is Q1. In fact, we can write it also as 3 by 2. nRTB is 2P0 V0 by applying the ideal gas equation. So nRTB is 2P0 V0 and nRTA is P0 V0. So it's 2P0 V0 minus P0 V0, which is P0 V0. So that is Q1. And Q2 is isobaric expansion. So process BC is isobaric expansion. So the value of Q2 is NCP delta T, and that means N into 5R by 2, because 5R by 2 is CP for monatomic gas, into TC minus TB, that's the change in temperature, and that is equal to 5 by 2 nRTC. nRTC will be 2P0 into 3V0, that means 6P0 V0. So 6P0 V0 minus nRTB is 2P0 V0. So this is coming out to be 5 by 2 into 4P0 V0, or simply 10P0 V0. So the efficiency eta we can now write here. Let's make use of the space which is available here, which is 2P0 V0, because work done is 2P0 V0. So 2P0 V0 divided by Q1 plus Q2, and that is equal to 10 plus 3 by 2, which is 11.5 P0 V0. And if we want in percentage, then we have to multiply it by 100, and then in percentage terms, this is what we shall get. So we can see that the P0 V0 terms cancel, and on simplification, this is coming out to be equal to 17.4%. So this is coming out to be 17.4%, and that means option 4 is correct for question 19. Let's go to the next question now. Question 20 says a Carnot refrigerator maintains eatables at 6 degrees C. If the room temperature is 30 degrees C, then the coefficient of performance is, okay. It's a pretty straightforward question based on the coefficient of performance of a refrigerator, and the coefficient of performance beta is given by the expression Q2 by W, which in fact is equal to Q2 by Q1 minus Q2. Now question arises as to what are these quantities Q2 and W, etc. Well, Q2 is the amount of heat extracted from the cold reservoir, that means from the refrigerator, and Q1 is the heat given to the hot reservoir, and W, the work that has to be done, is Q1 minus Q2. Now it turns out that this can be given as T2 by T1 minus T2, and in this particular case T2 is the temperature of the cold reservoir in Kelvin, and so the value of T2 is 273 plus 6, that means 279 Kelvin, and T1, which is the room temperature, is 273 plus 30, that means 303 Kelvin. So the coefficient of performance beta turns out to be equal to 279 divided by 303 minus 279, which is 303 minus 279, and this is coming out to be equal to 279 divided by 24, and this value comes out to be equal to 11.6. So for question 20, 2 is the correct option, which is matching with what we have got. Let's go to the next question now.